In this video, we're going to talk about different forms of quadratic equations. We're just going to start off with the most basic quadratic equation, which is just that y equals x squared. Let's think about what the graph of this looks like. I'm going to make a table for this graph, and I'm going to plug in the points -3, -2, -1, 0, 1, 2, and 3. Well, -3 squared is positive 9, -2 squared is positive 4, -1 squared is positive 1, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So we have points at 0, 0, 1, 1, 2, 4, and then 3, 9. As well as on the other side, we had one at -3, 9, -2, 4, and -1, 1. So our original y equals x squared graph is a parabola that opens up and has what we call vertex at 0, 0. Let's try another equation that's a little bit different. We're going to change what's happening to the x value here. So instead of just squaring x, we're going to square x minus 2 and see what happens to the graph. We're going to see how that changes the graph of y equals x squared now that we're subtracting 2 from the x value. And we're going to use these same x values to start with and see what we get. Well, -3 minus 2 is -5, and -5 squared is 25. -2 minus 2 is -4, -4 squared is 16. -1 minus 2 is -3, and -3 squared is 9. 0 minus 2 is -2, -2 squared is 4. 1 minus 2 is -1, and -1 squared is 1. 2 minus 2 is 0, 0 squared is 0. And 3 minus 2 is 1, 1 squared is 1. Let's take a look at the graph of this equation, y equals x minus 2 squared. At -3, we're at positive 25. So 25 is just off our graph here, actually. -2, 16. -1, 9. 0, 4. 1, 1. 2, 0. And 3, 1. Now, if we were to continue, okay, it would actually show the same symmetry as before. So I know that I can fill in the following points. This is the parabola, y equals x minus 2 quantity squared. And if you take a look, there was something important about this minus 2 here that we applied to the x. The entire graph from green to blue shifted or moved to the right 2 units. So subtracting 2 from the x moved us to the right 2 units, and it moved that point we called the vertex from 0, 0 over to 2, 0. So this number here, this 2, told us something about where this vertex, this turning point of the parabola was going to be. Let's take a look at a third example where we add something else to this equation. Let's try y equals x minus 2 squared plus 3. We're going to add 3 outside of those parentheses that are being squared. So we'll do the same thing. We'll draw another table, and we're going to use the same points. -3, -2, -1, 0, 1, 2, 3. Plugging in -3, right? The same thing's going to happen when we subtract 2 and square it. We're still going to get 25 again, right? -3 minus 2 is -5. -5 squared is 25, which is the value we got right here. And then we're going to add 3 to that. So 25 plus 3 is 28. -2, subtracting 2 and squaring, we're still going to get 16. But now we're going to add 3 to that. So we'll go up to 19. And the pattern's going to continue. We're going to get -1 minus 2, and then squaring it is going to get us 9, but then adding 3 will go up to 12. We'll continue with this pattern some more. So 4 plus 3 is 7. 1 plus 3 is 4. 0 plus 3 is 3, and 1 plus 3 is 4. Okay? So I took each of these numbers, and I added 3 to them, okay, to get these new y values over here. Let's see what that would look like if we graph it. I'm probably going to skip graphing this point negative 328 because it's going to be way off my graph. But negative 219 is going to be here. Negative 112 is going to be here. 0, 7, 1, 4, 2, 3, and 3, 4. And because of our symmetry, we know this will continue all the way in this direction. So I'll try and graph this in here as precisely as I can. So this new graph now that we've added a plus 3, is 3 units above where the blue one was. Okay, it shifted all of the y values. Remember these y values we were working with, it shifted them all up 3. Okay, it took whatever the x minus 2 squared value was and just added 3 to it. So now our vertex is at 2, 3. This point right here, remember our vertex. So that number here, the 2, right, that came from subtracting 2 from x, gave us this value of 2 from our vertex, for our vertex. And this value of 3 gave us the y value of our vertex. So this equation right here, y equals x minus 2 squared plus 3, is the equation of a parabola that we call vertex form. Because those numbers right there, the 2 and the 3, tell us exactly where the vertex is. We were just looking at y equals x minus 2 squared plus 3, okay, where the vertex, this is in vertex form, and it tells us that the vertex of our parabola is at 2, 3. There's one other thing we can do to transform this equation and put it in something that's still vertex form but is a different equation, and that is to add a coefficient in front of the quantity that's squared. Okay, so here we're doubling the quantity that comes out of the squaring and then adding 3. So let's make an xy table of this and take a look at what the graph comes out to be. I'm going to skip negative 3 in this case because we know that it's becoming a huge number, so I'm going to start at negative 2 and then we'll go up to positive 3. So let's graph this and see what it looks like. I'm going to skip, again, that point, negative 235, but negative 121 is all the way up here. 0, 11, 1, 5, 2, 3, 3, 5, and then because of the symmetry, we know we can keep going and put these points in. I'm also going to add in the original graph of y equals x minus 2 squared plus 3 before we put in that coefficient of 2. Notice here in comparing these two graphs that the vertex 2, 3 didn't change. Okay, there's still a 2 subtracted from an x and a plus 3 added out back. So the vertex of 2, 3 didn't change even when I multiplied by 2 out front. What did happen was that the graph got kind of skinnier, right? It looks like it goes up faster from that vertex, and that makes sense because once we plug in that x value, right, this time everything after we squared it got doubled, which means the y value went up faster, but it started in the same place, 2, 3. So our general equation for vertex form says y equals a times x minus h squared plus k. A is this leading coefficient that we had here as a 2, okay? And if that leading coefficient is negative, our graph is going to flip and be upside down. The h value and the k value here are the 2 and the 3 that we were originally working with. Those are the vertex. The vertex is at h, k. Now remember that when we subtracted 2 from the x, the graph moved to the right, not to the left. It didn't move left because it was a negative 2. It actually moved to the right. So whatever happens to the x, the opposite thing happens to the graph. So we need to keep this minus in here to indicate that that number is subtracted from x but then moves us in a positive direction. You're probably used to seeing equations in standard form, which is y equals ax squared plus bx plus c. This format is standard because everything's been multiplied out. There's no more like terms that we can simplify or combine. And if we were trying to solve something like ax squared plus bx plus c equals 0, then we can use the quadratic formula, negative b plus or minus the square root of b squared minus 4ac all over 2a. Right? These a, b, and c's come from the original ax squared plus bx plus c equation in standard form. And the form we just learned, or just looked at, was vertex form. And that one says y equals a times the quantity x minus h squared plus k. Right? Remember, that one's important because h comma k is the vertex. What I'd like to point out to you now is that the a in ax squared plus bx plus c and the a in vertex form are in fact actually the same number. Okay, they're going to determine whether the graph is stretched, right, pulled vertically, or if the parabola opens up or down based on whether a is positive or negative. And I want to show you why those are the same number by doing an example of switching something from standard form to vertex form. So we're going to work with the equation y equals 3x squared minus 12x plus 7, and we're going to use completing the square to put this into vertex form. To use completing the square, I'm just going to deal with the two terms that have x's in them, and then additionally, to do completing the square, we need to have a coefficient of positive 1 for our x squared term. So I'm going to take these two terms that I selected here and I'm going to factor a 3 out of them. So if I take 3 out of 3x squared, I'm just left with x squared, which is what I wanted. It has a coefficient of positive 1. And then negative 12x divided by 3 is negative 4x. And my plus 7 is hanging back out here. You can already see that this is starting to look like vertex form. To complete the square and put this into vertex form, I need to make this set of stuff in parentheses into a perfect square trinomial. So right now it's just a binomial, it only has two terms. So I need to add something here to make it a 3-term polynomial, a trinomial, and it has to be a perfect square so that I can write it as x minus something or x plus something squared. And I've also written this blank space out here because if I add something inside these parentheses, okay, to the right-hand side of this equation, I also have to subtract the same thing from that side of the equation to balance it out, right? If I add 3, I also have to subtract 3. If I add 21, I also have to subtract 21. It has to balance out or cancel out to be what it originally was. To complete the square, I need to take the coefficient of the x term, in this case negative 4, divide it by 2 and then square it. Negative 4 divided by 2 squared is going to get us negative 2 squared, which is 4. So I need to add 4 here, and now this thing in parentheses is a perfect square trinomial, and I'll be able in a minute to write it as some binomial squared. We added plus 4 inside the parentheses, but really we didn't only add 4 to this side of the equation. Because there's a 3 out here, and this 3 would be distributed back to this 4, what we really did was added 12. So in order to compensate for that, out here I need to subtract 12. Let me write that out for you in case it was a little confusing. If I distributed this 3, this would really say 3x squared minus 12x plus 12 and then plus 7. So this plus 12 I just added, to compensate for that I needed to subtract a 12. Now that we have a perfect square trinomial, we can say that x squared minus 4x plus 4 is really x minus 2 times x minus 2. And these two constant terms here, plus 7 and minus 12, I can combine to minus 5. So finally I can write this as y equals 3 times the quantity x minus 2 squared minus 5. That is now in vertex form, and we got there by transforming this standard form equation with the process of completing the square. Notice, as I said before, that this 3 and this 3 are the a value, and they are the same no matter whether you are in standard form or vertex form.